Okay, so now we're going to start into Unit 2, Multiple Linear Regression. As we'll see, all the intuition here is carried over from the last lecture, the last unit. The only difference is that we're going to be dealing with multiple features, and as we'll see, that changes a little bit about the way mathematically we have to deal with the problem. But the intuitions are all the same. So for this unit, the demonstration data set is going to be diabetes data set. So diabetes is a disease that impacts many millions of people. And so there's great motivation to understand if we can learn more about it. Can we predict this disease from things like biometrics like age, sex, body mass index, blood pressure, and other quantities that you get from a blood test? Can you use those things to predict in a diabetes patient, will their disease get worse or get better, and so on? Okay, so there's a relatively famous data set for this, used in a lot of machine learning classes. There are 442 data samples. There are 10 different features. Those 10 features are exactly this. So what we said before: age, sex, body mass, blood pressure, and then a bunch of other things that are typical outputs of a blood test. So, okay, how do we start out? We have to load the data. That's always the first step. It turns out that there's this wonderful package that we're going to be using extensively throughout the semester called Scikit-Learn. And Scikit-Learn has many routines, but it also has a few built-in data sets that are used very commonly. And so this is one of those data sets. So it's very easy to load it directly in Scikit-Learn. You don't have to use pandas or anything like that. So you just do datasets.load diabetes, and you get it, and then you can extract from it the data and the target. And as we'll see, this is going to build a matrix X and a vector Y that contains all the data samples. So when we look at X and we want to know its dimensions, we do this in NumPy using the shape command. And the shape command is going to return, in this case, two numbers: the number of rows, which is the number of samples, and the number of columns, which is the number of attributes or features. And we can print them out. We find 44 and 10, which are exactly the ones we would hope for this data set. Okay, so let's talk a little bit about how we represent our data. And we will be using this representation for the entire semester, but this is the first time we see it. So because we have multiple features now, as well as multiple samples, we can organize them all into a matrix. And so we have a matrix X, and when we look at that matrix, you can see as we go down, each one of these rows are different samples. And as we go across the columns, those are our features. We're always going to use N for the number of samples and D for the number of features. So when you look at this, we have D columns and N rows. So in this matrix, if I look at the ith row, I can call that Xi transpose. Okay, notice a few things. Because X is capital and boldface, we know it's a matrix. Because this X is boldface and lowercase, we know that it's a vector. And in fact, we know that this part is a column vector because it's always a column vector. And to make it a row vector, we have to put that transpose on there. So these rows here, we can label them like this. X1 transpose would be the first row. Xn transpose is the last row. And then we have many rows in between. Okay, so here, and then because whenever you see a non-boldface quantity, you know that's a scalar. So down here we have scalar values. This is like the first feature for the first sample, the first feature for the last sample, the D feature for the first sample, and so on. Okay, so that's how we organize our features. We organize our targets or our labels like this. We just stack them one on top of the other, the same direction as we stacked x, because n always goes down the rows, and here we have n going down the rows of this vector as well. So, so we have a feature matrix x and a target vector y. And finally, our data set is made of samples. You could think of the samples as one of these pairs. So, for example, x1, y1, that would be the first sample, all the way to the last sample, xn, yn. So in general, we have samples of this form, xi, yi. Okay, everybody good at this? All right. Okay, so when we think about doing prediction, imagine that there's some new vector of features that we will be given in the future. We haven't seen them yet. And at that time, our goal is to predict the target variable associated with those features, which we also don't know. So we can call those features x. We can call that target variable y. We know that we have d of these because d is always the number we use. And our linear model looks like this. So there's two things going on here. First of all, the true y is approximately equal to an offset plus a beta 1 times x1 plus beta 2 times x2 and so on, all the way to beta d times xd. Okay, notice that there's an approximately equal. But we're going to make a definition on this side that says that this is exactly equal to y hat. So we have y hat here, we have y here. So this is our prediction that we make of y, and this is the true y, which is probably not going to be exactly equal to y hat. How many coefficients do we have in this model? D plus 1, right? So don't forget, there's d features, but then there's also this intercept term. So we have d plus 1 learnable coefficients. So now the question is, how do we choose the best prediction coefficients? And we're going to stack them all into a vector, boldface beta. How do we choose that boldface beta given the data xi, yi? That's the question. And, well, I think time is up. We can continue with this next time. It's probably a good time to stop. So pause.